we're going to develop a set of equations that describe how a rotating object contains kinetic energy. And rather than, we're also going to develop the idea of rotational inertia, sometimes called moment of inertia, but I like to call it rotational mass. It kind of serves the same function as mass does in our equations, but for rotating objects. So, so let's first review a little bit. Right, we have V equals V naught plus AT, right? So this is for linear velocity. Equals our initial linear velocity plus acceleration times time. Well, we have analogous variables. Omega naught plus alpha times t, right? These rotate, we usually use, Greek letters to represent rotating variables. Well, and then we have, we have all the kinematic equations. I'm not going to write them all out, but now I'm going to show you this. We have Newton's second law expressed as the net force equals mass times acceleration, right? We're going to have a rotational equivalent to that. I'm just showing it to you now. We're going to kind of prove it over the next few minutes. I'm going to say the net torque is equal to rotational inertia times angular acceleration. And then we have kinetic energy equals 1/2 the mass times the velocity squared. Well, I'm going to show you something where the kinetic energy of a rotating object is equal to 1/2 the rotational inertia, the rotational mass, if you want to think of it that way, times omega squared. See how these are very similar? Look how similar they are. I don't know why we use capital I for rotational inertia. I would think that we would use some kind of Greek letter, but I don't know. They use I for rotational inertia. And I'm going to explain what that is. So let's get to it. Suppose I've got, I was demonstrating earlier, but I've got that rubber stopper on a string and it's swinging around in a circle. It's going around and around and around it goes. So here's the rubber stopper, and it has a certain mass, and it's on a string. Whoop, I didn't draw that very well, did I? On a certain string like this. And this circle has a radius of r. But let's say I hold it out and I push on it with a force. So I'm going to push on it. Oh, yeah, it does have velocity. But I'm going to push on it. I'm going to give it a force. Now this is a tangential force. Do you see that there's also another force on it? That is the tension force of the string, right? Which is going to give it a centripetal acceleration. That is the acceleration of changing direction. But here I'm going to speed it up. I'm going to make it go faster and faster and faster by applying this tangential force. And this tangential force is going to be equal to m times a tangential acceleration. Now this is not a centripetal acceleration. This is the acceleration that changes my speed. Okay? So now we have another acceleration, right? The centripetal acceleration is equal to v squared over r, but we're not talking about that right now. This is the force that's going to force this thing to go faster and faster and faster around this circle. Well, now I'm going to multiply both sides by r. R is the radius here. R times the tangential force is equal to r times mass times the tangential acceleration. All I did was multiply both sides by r. I can do that. Algebra lets me do that. But what is r times the tangential force? This is something we did last time. Do you remember? It's torque. This is the torque applied to this system. And since this is the net force that's causing tangential acceleration, we'll call this the net torque on our system. Now, is equal to R times M times the tangential acceleration. Well, but what is tangential acceleration equal to? Well, you might not remember this if you look back in your notes a couple of days. You'll see this, that the tangential acceleration is equal to R times my angular acceleration, where the angular acceleration is in radians per second squared. Now, hopefully you did the homework on that and you practice using those kinematic equations, and you understand what angular acceleration is. Well, now I can substitute this in here, and I get the net torque is equal to R times M times R times alpha. Well, that's kind of awkward. Let's simplify. Well, we're going to get mR squared times alpha. Well, look at this. mR squared. This is how much mass I've got in my rubber stopper, and this is what the radius is, and it turns out to be squared. This is this right here, this mR squared. We call this combination of mass measured in kilograms and a distance from the axis of rotation squared, this product of mR squared we call rotational inertia. Rotational inertia for this system. Now, what if instead of a rubber stopper, what if this was part of, what if I took a bunch of rubber stoppers and I just glued them together and made a wheel out of rubber stoppers? Just glued them together. Each little curl here is a rubber stopper. I'm trying to go fast here. Well, what would that change? R is the same, but all that would do is multiply the mass. Okay, and if I multiply the mass, I've got more rotational inertia. It would be harder to make that thing accelerate around the circle. I'd increase the rotational inertia. So it's a combination of mass times R squared that gives that to us. Now, what about kinetic energy? Or maybe, you know what, I can fit it over here. For kinetic energy, let me zoom out so I can fit it on there. Well, let's look at kinetic energy. Let's take a look at it when it was just this little mass, this one little mass right here. Well, when it's that little mass, we know what the kinetic energy is. It's 1/2 mv squared, isn't it? But if I want to express it in terms of the angular velocity, oh, let me do that. Hold on. The angular velocity, well, if an object is rotating around like this, I have an expression that tells me what the angular velocity is in terms of the linear velocity. It's like rolling motion and so on. V, our speed, equals R omega. Now, omega has to be in radians per second. This is meters per radian. This is radians per second. And so this is going to, since I know that the speed of this thing moving around this circle, v, is equal to r times the angular speed, or angular velocity, I can now make a substitution. And I can say k is equal to 1/2 mv squared. But v is r omega. Now look at this. Well, this is m, this is r squared, and this is omega squared. And what do you notice is right here again, just like we had with when we did torque. We've got mr squared. So that's rotational inertia. Now, we use the letter I, capital I, without a vector hat on it. It's a scalar. If you put a vector hat on it, people are going to think it's impulse. So leave the vector hat off. It's a scalar quantity. And when you have I like this is rotational inertia, and it has units of, well, look at the formula. Mass is measured in kilogram, and R is measured in meters, but it's squared, so kilogram, meter squared. Rotational inertia always has units of kilogram, meter squared. So now I can write my kinetic energy equation as 1/2 I omega squared. And now I can write my torque equation as I times alpha. The net torque acting on an object will give you an angular acceleration, but that angular acceleration depends on the rotational inertia. Now, the rotational inertia for a whole bunch of particles is easy. Let's say I had, let's do an example. Let's say I had two things like this, and let's say these are like little wires or rods or something, and they have very little mass. We're going to ignore the mass of the rods, because on the ends of the rods, we're going to put these massive objects like this. Call this 1, 2, 3, 4. And I'm going to try to twist this around. I'm going to put a twist on it. I'm going to torque it. Well, what is the angular acceleration I can get? Well, the net torque I need to cause an angular acceleration is equal to I alpha. But what is I? Well, I is equal to m1 r1 squared plus m2 r2 squared. Do you see what I'm doing? You can just sum all of these together. Now we have a shortcut way of doing this, and I'm going a little faster than I'd like to, but we only have like 3 minutes left. I'm going to sum have you seen summation notation before? MIRI squared. This is the definition of rotational inertia for a system of particles. Now this only works if these all are fixed. You know, they're not moving with respect to, they're moving around like this, but they don't, it's like if I move the paper like this, they're like, it's like a rigid object. Okay, yeah, do that in your notes. Now, what if I had an extended object? And I wanted to know, what is the rotational inertia about here? Now, you don't even need to write this down. But whenever you see a summation like this, you can use calculus to say it's r squared times a little tiny chunk of mass, dm. Like here's a little tiny chunk of mass, here's its r. You take that r squared times a little tiny chunk of mass, and then you sum them all up. You break this into an infinite number of little tiny masses, and you sum them all up, and you have the rotational inertia. This is how you calculate the rotational inertia for an extended body. But you don't have to do that in this class. Now, if you take AP Physics C next year, those of you who are juniors, we'll do this, because we're going to use calculus. And I hope some of you will do that. But Where'd it go? In this book, we've already got, they've done it for you. This is on page 208. I'm going to zoom in here. And these are all on page 208. And do not copy these down. You will not need to copy them down on your equation list, but you'll need them for your homework. If the shape looks like one of these shapes, then you use this equation, 2/5 mr squared, to figure out what the rotational inertia is. Like if it's a solid sphere like this, the rotational inertia will be 2/5 of the total mass times the radius of that sphere squared. And you can use that to solve problems. Now we don't have time to work an example here, but these are the ideas you're going to use for the homework. And we'll spend some class time working examples and so on next class. That is all.